Okay, this is the video to solve homework problem 12-29, which is on black body radiation. So 12-29. And the problem says that daylight and candlelight may be approximated as black bodies. So we know we're doing a black body problem, so I'm just going to jot that down. And it says that they have temperatures of daylight, so I'll write T day is 5800 Kelvin, and T from candlelight is equal to 1800 Kelvin. It says determine the radiation energy in watts per meter squared emitted by both lighting sources, daylight and candlelight, within just the visible light region. So we want to look, we want to try and find the emitted energy, which is E sub B for a black body. This is the emittance of a black body, but we only want it for a range of 0.4 less than lambda less than 0.76 micron. So this is what we're looking for. Okay, so there are two parts to this problem. Part A says do that for daylight, and part B says do that for candlelight. So let's start. For A, we are doing daylight, and we're only looking for the emittance in a particular range between lambda 1 equal to 0.4 micron and lambda 2 0.76 micron, right? And this is the visible range. So we know that we could find our fractional emittance. We have this symbol lowercase f, which is just equal to the emittance at the particular wavelength. So we have from, let's say, 0 to lambda 1 of the emittance for that wavelength. And it's the fraction, the little f is just the fraction because we're comparing the emittance that is from the integral that goes from 0 up to a particular lambda divided by what it would be if it was for a black body over the entire spectrum of all wavelengths. So for this problem, we're trying to find a range. So we could, if I can draw this out, if we were to plot lambda on the x-axis and this fraction over here, we would see that we would get a curve that looks something like such. And we can go to these tables, table 12-2, which does this integral for us, okay? And it displays values for little f if we give it values of lambda times the temperature. And what that does is it does the integral from 0 all the way to lambda. So let's say we have lambda 1 and some lambda 2, right? We look on the chart, so this is pretty much f, right? So when we look on the chart for lambda 1, what we would be given is this entire area all the way from 0 up to lambda 1. Then we can look up the integral, right, which is the area under the curve for lambda 2, which again is going to be all the way from 0 but now up to lambda 2. Okay? So we see if we subtract the two areas, we'll find what we are looking for, which is just the fractional value between lambda 1 and lambda 2. Okay? So that's what it looks like in kind of in a diagram type form, but we can also write it like this: f from lambda 1 to lambda 2 just equals the f of lambda 2 minus the f of lambda 1. Okay, so that's what we're going to use. So we'll go ahead and start to plug in some of our values. So this is, again, part A for daylight. And we need to find the value of lambda 1 times t. So we have our lambda 1 times our t daylight, and that's just equal to 0.4 microns times 5800 Kelvin, and that is equal to 2,320. And then we also need lambda 2 times t day, and that is equal to 0.76 times that 5800, and this is equal to 4408. Okay, then we'll go ahead and we'll go to that table. This was table 12-2, and we would find that Okay, then we would find that little f that goes from 0 to 0.4 is going to equal 0.124509, and then little f that is the integral from 0 all the way to 0.76 is going to equal 0.550015. So to find the fractional only within the visible spectrum, 0.4 to 0.76, it's just f from 0 to 0.76 minus f 0 to 0.4, which is equal to 0.550015 minus 0.124509. So we see that this is equal to 0.425506. Okay, so now we have what our fractional emittance is. So the next thing we need is we need to know what our black body radiation within this range is. And we want this evaluated at 5800. So we know that for a black body, we have sigma times T to the 4, sigma being our Stefan-Boltzmann constant, times temperature to the 4th, times just what our fractional value is. So this is going to equal 5.67 times 10 to the minus 8 times 5800 raised to the 4 times 0.425506. So punch that into our calculators, and we get that the emittent radiation in the visible light spectrum for daylight is 2.73 times 10 to the 7 watts per meter squared. So that's part A. And we'll just do the same thing for part B, which is for candlelight. So we have lambda 1 times T candle and that's equal to 0.4 times 1800, which is equal to 720. Then we have lambda 2 times T candle, which is equal to 0.76 times 1800, which is equal to 1368. Look these up on the chart. We get F from 0 to 0.4 is going to equal 0.0000096, and F from 0 to 0.76 is going to equal 0.006885. So we can find what our fraction is just between 0.4 and 0.76, and we know we just subtract them, so we have 0.006885 minus 0.10000096. So this is equal to 0.006875. Then we have our black body radiated between 0.4 less than lambda less than 0.76 equals lambda t to the 4 times F, and this is 5.67 times 10 to the minus 8 times T, which is 1800 to the 4 times F, which is 0.006875, and we will find that the emitting energy for the candlelight is 4090. So 4090 watts per meter squared. And that's it. That is the answer to 1229.